calculus today, which is really exciting. We're going to start by, I'm going to give it to you, and then we're going to use it, and then we will prove it either at the end of the lesson or in a separate video. And you'll like the proof because it brings together the idea of the mean value theorem along with adding up rectangles and this Riemann sum thing that we looked at last time. But really, in Cal 1, and as engineers or computational mathematicians, you're going to need to be able to apply the fundamental theorem. So we'll look at that first and see how great it is, what it is that you're learning. So this is a huge day for you in mathematics. Go home and talk to your family and your friends about how today you learned the fundamental theorem of calculus and how totally awesome it is. So it's a big day. Okay. So it says, what is the fundamental theorem of calculus? And we will begin. And we're going to write it. Suppose. Oh, sorry. I got to get the computer on for my friends at MCC. Okay. Suppose f is continuous on a closed interval from a to b. Okay, so we have a closed interval from a to b, and our function is continuous. Part 1 of the fundamental theorem of calculus tells you if the function g, and this is really interesting because it's been a while since you've learned a new function. And I'm going to give you a function that's defined by an integral. And it's totally legal, it's just weird. So the function g is defined by, okay, here's this new function. You remember when you learned about the squaring function, it was something to the square. You put a little 2 on it. But that was a definition. When you wanted a number to be squared, you raised it to the 2 power. That was defined for the first time in whatever grade you were. All right, so here's a new function, g, in terms of x. It's going to be defined by an integral from a to, there's my variable, x, f of t dt for all x in AB. Okay, so that's my function. Then, if that's the function, then g is an antiderivative of f on the interval from a to b. Okay? So all this is really saying is that if I take the derivative of g with respect to x. So this is g. If I take the derivative of g with respect to x, I'm going to get exactly just little f of x. Okay? Which is this stuff inside with an x in it. Okay, so that's a new function that's defined as the antiderivative of f. Okay? So this is means. Right, well that's not, I mean, it doesn't seem that cool. It kind of gets cooler later, especially in your physics and your calculus, when you can define a function as the antiderivative. You start to see the applications of that later. Part 2 is the really cool part.
Excuse me?
Yeah?
Can you explain the last part one more time?
Okay. If g of x is equal to the integral from a to b, this is just a function. I've just defined it to be this integral from a to x of f of t dt. Then we can say that g is an antiderivative of f on AB. So if you were to take the derivative of this function, g of x, you're just going to get the little inside right here. Okay? Does that make sense? It'll make sense, probably more sense with an example.
Yes, thank you.
Okay. But basically, you take the derivative of this, you get that. That's what they're saying.
Okay, thank you.
Okay, with an x. And you may have to use a chain rule. We'll look at some examples in a second. All right, part 2 is the really cool part. You ready? So this
Yes.
is awesome. All right, if f is any antiderivative of little f. So big F is the antiderivative of little f on AB. For example, if little f is x, then big F is x squared over 2 plus some constant. So it could be x squared over 2 plus 5 or x squared over 2 plus 12 or whatever, okay? Big F is the antiderivative of little f. If that is true, then the definite integral from a to b of little f of x is exactly big F of b minus big F of a. So all this is telling you is that if you want to evaluate this integral, find the antiderivative and then do f of b minus f of a. So last lesson we learned that this, when f of x is positive, is the area under the curve. So if you know the area under the curve, if you know the antiderivative of the function, then you can actually calculate the area under the curve for very complex looking functions that you never could find the area of the curve before. So for example, the integral from a to b of x squared dx, visually, what does that mean? Well, visually that is the function f of x equals x squared, right? And the integral from a to b, we learned last time, that means the area from a to b. And I just arbitrarily picked them to be positive, but I could pick it over there too. That's finding the area under the parabola. How do you do that? Well, you could do it with the method of exhaustion, just more and more and more rectangles, and you get an approximation to it. But you can actually, this is telling us, the fundamental theorem is telling us we can find that exact area by calculating the antiderivative of x squared and then doing the antiderivative evaluated at b minus the antiderivative evaluated at a. So what is the antiderivative of x squared? Well, f of x is equal to x cubed over 3 plus c. But since it's any antiderivative, I don't have to put the plus c. I can just think it's plus 0. And then if I do f of b minus f of a, that will just mean b cubed over 3 minus a cubed over 3, which we did last time. We talked about last time. Okay, so that's pretty exciting. So now for any parabola, you can find the area under it using the fundamental theorem. Okay, so let's do some examples. It says use the fundamental theorem of calculus to evaluate the following. Okay, so right here, this is your f of x. All right, who can tell me what the antiderivative of f of x is? Who can tell me big F of x? X to the fourth over 4 minus
x squared.
It's 2x squared over 2, which is just x squared, and then plus 3x. And then normally you have a plus c, but we don't have to put the plus c here because we're going to do a definite. All right, so this antiderivative, or this definite integral, is f of b minus f of a, where b is the top limit and a is the bottom limit. So this is going to be big F of 2 minus big F of negative 2. All right? But we know what big F is. It's the antiderivative here. So this is going to be equal to 2 to the fourth over 4 minus 2 squared plus 3 times 2. That is big F of 2. And then we're going to do minus negative 2 to the fourth over 4 minus negative 2 squared plus 3 times negative 2. And that is, do in blue, F of negative 2. Okay? And then you can just clean this up. 2 to the fourth is 16 over 4, which will be 4 minus 4 plus 6 minus Okay, this is still 4, and then that's going to be minus 4 minus 6. So you get the 4's cancel here and here. 6 minus negative 6 is 12. So the area under the curve of x cubed minus 2x plus 3 from negative 2 to 2, if that's positive, that area is 12. Let me see whether, if we look at that, that may not be positive on that interval. And so I'll talk about something else if it's not. X cubed minus 2x plus 3. If we graph that, let me do a standard window. Yeah, on the interval from negative 2 to 2, it is positive. So if I change my window to like negative 3 to, stop it. Okay, window, negative 3 to 3, and this can be like negative 5 to 5. I was looking at this area, well, there is a little bit of negative in there. It looks like it, negative 2. So it's not going to be quite this. It's going to be all of this area, and then they're going to actually subtract out a little bit there. So because it's negative, the area is, the integral is negative when you're below the x-axis. So it's, if you were to look at this together, if you wanted to get the part, you'd need to find this 0 and then make that part positive if you wanted to find the total area. But anyway, kind of interesting. Okay, so Robinson, do you want to try number 3 for me? Do you want to tell me what that one's going to be? Can you start by telling me big F of x? Are y'all there? What are you doing? You're unmuting? What's happening? They're passing the mic. Just unmute, hit unmute, and tell me the antiderivative.
Oh, that's easy. 2/3.
2
Add
thirds
1
x.
to 3 halves.
Okay. 2 thirds x to the 5 halves.
You were unmuted.
It is.
Go.
2 thirds x to the 5 halves.
2/3 x to the 5 halves, that's your answer?
It'd be 5.
No, no.
2/5 x
I
to
like
the
that
5
better.
halves.
Okay, so you add 1 to the exponent, which is going to be 5 halves, and you put it over it. So that, which reciprocates 5 halves, which makes it 2/5. So this is 2/5 x to the 5 halves. And this is new notation here. Once you've done the antiderivative, you draw a little line, and you'll go from a goes from 0, and then b equals 5. A lot of times you'll see me do that, and sometimes you'll see me not even write the a and the b. Okay, and so what that means is that you're going to do f of 5, f of b minus f of a, which is 0, which means you're going to do 2/5 of 5 to the 5 halves minus 2/5 of 0 to the 5 halves. Okay? And 2/5 of 5 to the 5 halves means the square root of 5 to the 5th, right? Which means there's 5 5s under here. And a square root, and this of course is 0, a square root is a 2-for-1 deal. Are y'all right? So if you do the square root of 5 times 5 times 5 times 5 times 5, you can pull 1 5 out here for 2 of these, and you can pull another 5 out there. So you're going to have 5 squared on the square root of 5, or 25 on the square root of 5. So this is 2 times 25 on the square root of 5 over 5. And then 5 goes into 25 5 times, and 2 times 5 is 10. So this is 10 on the square root of 5. Are y'all okay with the algebra from days gone by? Okay, let's look at this one. What is the antiderivative, MCC? What is the antiderivative if this is your your derivative, what function has as its derivative 1 plus cosine x? What is my big F of x?
X plus sine x.
Good, x plus sine x, and you're going to evaluate that from 0 to pi. And so this is going to be f of b minus f of a. That's how we compute it, okay? So that means f at pi minus f at 0. Well, f at pi is pi plus the sine of pi. And then minus f at 0, which will be 0 plus the sine of 0. Okay, what is the sine of pi?
0.
The sine of pi is 0. The sine of 0 is also 0. So the answer to this one is just pi. So if you wanted someone to tell you what's another way to represent pi, you can say the integral from 0 to pi of 1 plus cosine x dx. And they might say, well, we're 3.14. And you're like, yeah, that works too. Okay, on this one, when you're doing a problem like number 5, what you want to think about is go ahead, if you can pull anything out in front, go ahead and do that. Like that fraction's stressing me out. So I'm going to take the 1/2 out in front, and I'm going to go from negative pi over 3 to pi over 3 of 1 minus cosine 2t dt. Does that make sense? Because remember, constants just tag along. Okay, Robinson, what is the antiderivative of 1 minus cosine t dt?
Here goes the same side.
Cosine t or cosine 2t?
No, sorry, cosine 2t.
Okay, so that'd be the derivative is 2 and then times that by negative cosine b negative sine. Right? So we're x minus sine.
Minus sine 2t?
2 sine. 2
X minus 2 sine 2t? Is that what you're saying? Yeah.
No, they're 1/2.
How about t?
Or 1/2. Okay.
I mean,
Minus.
t, sorry.
I don't want you to confuse the derivative with the integral. It seems to be a disease that has infected Robinson. Because on the last problem, you told me 2/3 x to the 5/2, which means that you confused the derivative and the antiderivative, right? And that disease has now processed down to this one. So can you please tell me the antiderivative
So is the
of
answer
cosine 2t?
Is it 2, or is it t minus t sine 2t?
Okay, so you want to say t minus t sine 2t?
Yes.
Can you take the derivative? This is your f of x. So can you take the derivative of this for me?
It's supposed to be 1/2 sine.
Well, you can.
1 minus.
1/2 sine. Yeah.
You got to do a product rule.
That's 4.
So that's a big fat no.
Yeah.
All right, maybe we're not quite where I want you to be. If you know that the function is x to the 3rd, then the antiderivative of that is what? What function has x to the 3rd as its antiderivative?
1/2 x squared.
This?
Antiderivative. It's
It'd be
Wouldn't it be
1/4
1/4
x to the
x
4th.
There it is. Okay, x to the 4th over 4. Right? Okay. See, if I take the derivative of this, I get to x cubed, right? Okay, now you guys told me 2 sine 2t. If I take the derivative of this, will I get minus cosine 2t? Or even with a minus here? Yes or no? What is the derivative of this function right here? Isn't this?
We can't see the whole problem. Can you just
Okay.
oh, okay.
What is, if your function is sine -2 sine 2t, what is the derivative of that? If that's your big F of x, what is little f? What is the derivative of that? F prime of x, which is little f, or t, sorry. What will the derivative of that function be? You can do it. You're good. I've seen hundreds on derivatives. Tell me what the derivative of this function is.
What was it again? Negative 2 cosine 2t.
And then don't forget your chain rule.
Times 2t. Times 2t.
Okay, so -4 cosine 2t, right? Okay, now that's not what you're trying to get. You're trying to get negative cosine 2t. You got -4 cosine 2t. So I'm going to say that this is not the correct derivative. -2 sine 2t is not the correct antiderivative for this function. Because when I take the derivative of it, I do not get negative cosine 2t. So you're trying to come up with the function that when you take the derivative of it, you get negative cosine 2t. So you knew that when you took the antiderivative of 1, you would get t. That's correct. What function do you take the derivative of to get negative sine 2t? I mean, to get negative cosine 2t. What function? Still nothing? You can unmute. Are y'all talking about me? Or are you talking amongst yourselves? Or are you just staring blankly at the screen?
Kendall says sine 2t.
Okay, what's the derivative of sine 2t? If this is big F.
Cosine 2t. Say 1/2 sine.
She can hear you.
Yeah, she can
Say
hear
it
you.
loud.
Just say it.
Say 1/2 sine 2t.
There it is. There it is. There it is. Thank you.
That's what he said in the video.
What? Did you say that sometime in the beginning? I never heard that, 1/2. What I heard was the 2 in front, which is combining, it's mixing up the derivative and the integral. It's a classic mistake. Okay? Do y'all see me? Okay. All right. All right, and we're going to do this from -pi/3 to pi/3. Okay, so now what we do is we plug in and we have 1/2. So this is our A and this is our B. Okay, so you're going to do f of B minus f of A, and remember you take 1/2 of it. Okay, so this is going to be 1/2 f of B, which is pi/3 minus the sine of 2 pi/3 divided by 2, that's your f of B, minus negative pi/3 minus the sine of negative 2 pi/3 over 2. Okay? And this is equal to 1/2. So who can tell me what the sine of 2 pi/3 is? Okay, the sine of 2 pi/3 is the square root of 3 over 2. So this is going to be minus square root 3 over 2 over 2 minus, remember you're going to take that 1/2 of the whole thing, negative pi/3 minus the sine of negative 2 pi/3 is negative square root of 3 over 2 over 2.
Bye, Miss Brooks.
Are y'all leaving? Why are y'all leaving?
Yeah, we got to go to the senior meeting.
Okay. See you later. Oh, what happened with the penny thing?
Nothing. It just kind
Nothing?
of went over the floor. I mean, nothing really happened.
Aw, nobody got mad or anything?
No, not really. They just cleaned him up and they're gonna like donate him to like leukemia or something.
Oh, well, that's good.
So,
All right.
yeah.
All right, so this is pi over 3 minus the square root of 3 over 4. And this, when you distribute the negative here, notice you're going to have plus pi over 3, and then it's going to be minus the square root of 3 over 4. Do y'all see that? Because it's a plus here, but then you're subtracting it. Yes? Okay, and so then negative square root of 3, did I say that? Did I say that right? Yeah, it's going to be minus. Okay, so we have the pi over 3 and the pi over 3, which makes 2 pi over 3, and the negative square root of 3 over 4 and a negative square root of 3 over 4, which makes negative 2 square roots of 3 over 4. And then we're going to take half of all of that, so it's going to be pi over 3 minus the square root of 3 over 4. Does that make sense to y'all?
Yeah.
Because there's 2 here and there's 2 here, but then I take half, so then there's only, that's all it is. Okay, so now on this problem, I think I am going to pick on you to help me, Alan, simplify this before I work it. I'll give you a hint. 1 over the square root of u minus the square root of u over the square root of u, right? Mm-hmm. Okay, and so before I work it, how would I clean that up? How would I write 1 over the square root of u? I'll give you a hint. U to the negative 1/2 power?
Yeah.
Okay. Square root of u over square root of u is? Yes, it is 1. All right. Okay. Now, antiderivative, big F of u is, all right, the antiderivative of u to the negative 1/2. We're going to add 1 to the exponent. So negative 1/2 plus 1 is 1/2, and we're going to put it over that. When you divide by a half, it's like multiplying by 2, right? So this is 2u to the 1/2 minus the antiderivative of 1, which is u, and we evaluate that from 9 to 4. This one's kind of weird because your b is smaller than your a, but I mean, it's okay. So you're going to do f of 4 minus f of 9, because that's your b. So it's going to be 2 onto 4, the square root of 4 minus 4, that's f of b, minus 2 on the square root of 9 minus 9. That's your f of a. Okay, the square root of 4 is 2. 2 times 2 is 4, minus 4 is 0, minus the square root of 9 is 3. 3 times 2 is 6. 6 minus 9 is negative 3. So your answer is 3. Okay? All right. Antiderivative from 1 to 2 of 1 over x e to the negative x minus e. Anyone? Okay, so who wants to do this one? What's the antiderivative of 1 over x? Right, it doesn't work. It can't be x to the 0 over 0. ln. There it is, thank you. This is the ln of the absolute value of x. All right, what's the antiderivative of e to the negative x?
Or negative e to the negative x over negative.
Right, well, this minus is what you're handling, I guess, right there. And then it is e to the negative x over negative 1. So we can just make that positive, right? And we're going to evaluate that from 1 to 2. I'm just, it's like I want rum in my coffee. I think it would be, I'm a little frustrated with the lack of quick antiderivatives, but I should let it go because I know that you just learned them and it's not my fault. I mean, it's not anybody's fault except mine perhaps because I know them really well, but I need you guys to know these. We took a test over it, right? Okay. This is f of b minus f of a. f of 2 minus f of 1, where this right here is your big F of x. I cannot stress how much I want this homework done when you come to class on Monday. Okay, so this is going to be the ln of 2 plus e to the negative 2 minus, that's f of 2, f of 1, which is the ln of 1 plus e to the negative 1. All right? So this is the ln of 2 plus 1 over e squared minus, what's the ln of 1? The ln of 1 is 0, because that means e to what power is 1? And so that would have to be any e to the logarithm of 1, no matter what the base, is always 0, because it means raise a number to a power, and give me the power that you raise a number to get 1, and it's always got to be 0. Okay, and so then this is minus 1 over e. And that's the answer. So it's kind of interesting. I mean, once you get past, and you will, once you get past the doing it and remembering all the formulas and such, and think about what you're talking about, this antiderivative, which is in some sense area, as long as the function's positive. If it's not positive, then it's like the additive of the, the area, like some negative, some positive area or whatever. But it is some sort of geometric representation that you can get in your mind. And it's so odd to think that you can have these functions that are transcendental, meaning they, you can't even plot. We know what e to the x looks like, but how is it that we know? I mean, we can't ever plot those points. And here we are getting an area that is so odd. The ln of 2 plus 1 over e squared minus 1 over e. It's not like 5. It's not like the area is 12, which, I mean, we liked it on this one, this area was 3. I mean, how cool is that? That's pretty interesting. But notice again, you're going from 9 to 4. So if you went from 4 to 9, what would the area be? That's a good question. Good, negative 3. That was from last time. So it's not really area, but it is sort of still a visual that you can get. And then, here, this curve, you can probably imagine what this curve looks like, the cosine curve. It's going to be shifted up half a unit and then reflected, so it's going to be like a little hat, kind of, and from negative pi over 3 to pi over 3, so just kind of looks like this, something like that. And you're finding that area right there to be pi over 3 minus the square root of 3 over 4. It's just fascinating in a sort of purely mathematical sense. And there's applications to this, I promise. The baby application that we looked at was if I know velocity time, I can find position. But there's more applications to it in probability and statistics and just all over the place. Okay. This is my favorite function, so if you want to make me happy right now, it's your favorite function too, and you know it. What function has as its derivative 1 over 1 plus x squared? I'm going to factor that 4 out, so I have 2 to 4, and it's 1 over 1 plus x squared. It's Mrs. Brooks' favorite. She told you it comes up a lot. Which one was it? What function had as its derivative 1 over 1 plus x squared? Say you don't want to disappoint me, but you can't remember it. Do remember that you have a formula sheet somewhere. I can't remember where it is. I've got it. I mean, I gave it to you online, right? Let me see if I can find mine. I thought I labeled it. Tables. There we go. Okay. There is a formula sheet, and so we can come down here to these integrals, and we can look and see if there's one that looks kind of like it. It's a little bit more disguised, but I could tell you that it is in the first column. And it looks kind of like the one we're looking for was 1 over 1 plus x squared. Which one looks kind of like that? 17? 17? Yeah, this one. And that's right. Your a is 1 here. The a is just a constant. And so it is the inverse tangent. This is that inverse tangent function. This is the the derivative of the inverse tangent. The derivative of the inverse tangent. is that, you can see it right here, arctangent is 1 over 1 plus x squared if you just have x. Okay, so this is the inverse tangent of x, and so we will say that this is just going to be 4 times the inverse tangent of x evaluated between 2 and 4. Okay, so this is going to be 4 times the inverse tangent of 4 minus the inverse tangent of 2. And you can't, I mean, you can evaluate that with your calculator or whatever, but that's all it is there. You can't, there's nothing pretty. The inverse tangent of 1 is pretty because that's pi over 4, you know. But we don't know the inverse tangent specifically of 4 or 2. So again, you're like, well, how does my calculator know? And again, you're saying, because I have to learn Cal 2. Okay, so this is really cool. It looks scary, but it's actually really cool. It says find the derivative of this by evaluating the integral and differentiating the result, and by differentiating the integral directly. Okay, so I'm going to evaluate the integral and differentiate the result. So what they're saying is I'm going to work from the inside out. So first I'm going to compute the integral from 0 to x of 1 over 1 plus t squared dt. And then I'm going to take the derivative of it. Okay? So I just did this one. This is going to be the inverse tangent of x minus the inverse tangent of 0. So this is the derivative with respect to x of the inverse tangent of x minus the inverse tangent of 0. Now, hopefully you remember that the inverse tangent of 0 is just 0. Do you remember that from, yes? Okay. So the derivative with respect to x of the inverse tangent of x is what? Yeah, it's right there. You're doing good. That's a good step. Look on your sheet. Tell me what the derivative of the inverse tangent of x is.
U prime over 1 plus u2.
Okay, where u here is x. So the derivative of x is just 1. So this is going to be 1 over 1 plus x squared. Right? Okay. Do you see something like that anywhere? Yeah. The first part of the fundamental theorem of calculus told me that if I take the derivative of some function, it will be this function evaluated at when I plug the x in. Now, if I had like a 5x right here, I actually have to take the derivative. I have to use a chain rule. So I'd have to say times 5 if this were not just x. Okay? But otherwise, I can jump from this step to this step immediately by part 1 of the fundamental theorem of calculus. Okay? The derivative of the integral is the integrand, this little guy, with an x put in it and maybe a chain rule necessary. Does that make sense? So that, first we evaluated the integral, which is what we did right here, and differentiating the result, which is what we did there, and then differentiating the integral directly. That means using part one of the fundamental theorem, the derivative with respect to x of an integral, they undo each other. And so it's like they kind of cancel out, but you do have to kind of shove the x in there. Does that make sense? So, because this is with respect to t, so it's going to be 1 over 1 plus x squared. And so if this right here was not just x, if it was like 5x or 12x squared or something like that, then you would have to differentiate that. You'd have to use a chain rule and multiply by that. So we'll do another one, and it'll show you. So for example, this one, let's do it both ways. Okay, so let's first evaluate this. So evaluate the integral. So we're going to evaluate the integral from 0 to the tangent of theta, secant squared y dy. Okay, now what is the antiderivative of secant squared? What function has as its derivative secant squared?
Tangent.
Right. So this is the tangent of theta evaluated from 0 to the tangent of theta, right? Okay, so this is weird, but this is the tangent of theta, that's f of b, minus the tangent of 0. But the tangent of 0 is just 0. So this integral is the tangent of theta. Okay, so that's the first thing. That's evaluating the integral. Now let's differentiate the result. So now finding the derivative with respect to theta of the tangent of theta, you have to use the chain rule, right? The derivative of the tangent is secant squared theta, right, times the tangent of theta, and then, the derivative of the tangent is secant squared u, where u is tangent theta, and then times the derivative of the u, the derivative of tangent theta is secant squared theta. Are you okay? Yes. But using part 1 of the fundamental theorem, when you are asked to find the derivative with respect to theta of an integral from 0 to tangent theta of secant squared theta, y dy, part 1 tells us that it's just going to be this, evaluated at this, but you'll have to probably take the derivative of this if it's not just an x. So this is going to be secant squared of, instead of y, it's going to be tangent theta times the derivative of tangent theta, which is secant squared theta. You putting it together, sort of?
Oh, yeah.
So it's easy. Like you just write this with this top part in it, and then times the derivative of that, if it's needed. Like on this one, it wasn't needed because it was just x, so we didn't need the derivative. We just evaluated this at x, and the derivative of x was just 1, so we didn't need it. But on this one, we just wrote this with that in it, the tangent theta in it, and then times the derivative of the b, if that's from a to b. Okay. So if you're asked to find the derivative with respect to x of the integral from the square root of x to 0 of the sine of t squared dt, all right, well, the first thing you ought to do is put it exactly in the form of the fundamental theorem. The fundamental theorem went from a to x, right? So I need to switch my limits. Do you remember in section 5.3 we learned how we can switch our limits, though, right? We just make it negative, okay? And so I can say that this is the same as the opposite of the derivative with respect to x and 0 to square root of x sine t squared dt, right? Okay, and now the fundamental theorem tells me that this derivative is going to be the sine of the square root of x squared times the derivative of the square root of x. But you just write this with this in it and then do the derivative of that. Okay, so, and you still have this negative that's going to tag along. So this is the sine of the square root of x squared times the derivative of the square root of x, which is 1/2 x to the negative 1/2. And so this works out to be negative sine x squared over 2 on the square root of x. Not x squared, just x, because the square root of x squared is just x. So they're actually kind of fun. I mean, they're really not that hard to see. That's that first part. Okay, so say we want to find the total area between the region x cubed minus 3x squared plus 2x and the x-axis on the interval from 0 to 2. Okay, and I gave you a hint that you're going to want to graph it first, so let's go ahead and do that. So we've got x cubed, I think I said squared, minus 3x squared plus 2x. And we want to look at it on the interval from 0 to 2. So I'm going to change my window to 0 to 3 will probably be okay. I'm going to change my y max. I'm going to make these smaller. I'm going to go from -1 to 1. So weird how this gets funny. Okay. Now on the interval from 0 to 2 so I'll pull this over. No, it probably won't. It won't show up. Okay, so on the interval from 0 to 2, it's exact at 2, it's 0. That's 8. See, 2 cubed is 8. 2 squared is 4 times 3 is -12, and then plus 4. So that is going to be 0. So and at 1, you also get 0. So it has roots at 1 and at 2. And it looks like it has some part here, and then it has some part here. You don't necessarily, there's not symmetry necessarily. So what we have to do is integrate from 0 to 1 x cubed minus 3x squared plus 2x dx. And then we have to add to that the absolute value of the integral from 1 to 2, because this integral is going to be negative. Does that make sense? Because it's underneath, you're actually going to end up with a negative, but it's just the absolute value of it. So we're going to do the absolute value of the integral from 1 to 2 of the same function, x cubed minus 3x squared plus 2x dx. Okay, so what's our antiderivative? Well, this is going to be x to the 4th over 4 minus, it'll be x to the 3rd over 3, but it's 3 times that, so it's just x cubed plus x squared over 2, which is just going to be x squared, and you're going to evaluate that from 0 to 1, and then you're going to add to that the absolute value of the same antiderivative, so x to the 4th over 4 minus x cubed plus x squared, evaluated from 1 to 2.
So that's where the finding concave, convex stuff would be really useful if you didn't have a calculator. Find out where it's below 0, below 0.
Yeah, well, you really actually need to figure out. That's where Newton's method would be real useful. I mean, there's a lot of different techniques that would be, if you didn't have a calculator to approach this, because you need to figure out where it's exactly equal to 0, so you can know where your limits are. And so there's all kinds of techniques to figure out where a function equals 0. It can be a real challenge, especially a cubic function. Okay, so I can put 1 in here for my f of b, so this is going to be 1/4 minus 1 plus 1. Y'all notice when I put 0 in, I'm just going to get 0. Okay, so that's that first antiderivative. Plus, now this is the absolute value. This is going to be f of b, so it's going to be 2 to the 4th over 4 minus 2 cubed plus 2 squared minus, and then when I put 1 in, I'm going to get 1/4 minus 1 plus 1. And I'll take the absolute value of that. Okay, so this is 1/4 plus, let's see, 2 to the 4th is 16 divided by 4 is 4. So this is going to be 4 minus 8 plus 4 minus 1/4, and then take the absolute value. So 4 minus 8 plus 4, that's 0. That's negative 1/4, which will be positive 1/4. So it's 1/4 plus 1/4, or 1/2. So that's kind of cute. And so on this one, it did turn out that those regions were symmetric, but you don't always know that. You could do some derivative work, though, and see where the max and mins were and kind of argue that, but whatever. Okay. Find the area of the region bounded above by the line y equals 2 and below by the line, or by the function 1 plus cosine x on the interval from 0 to pi. Okay, Now, when you look at this function, the line y equals 2 is this line right here. This is the line y equals 2. Now, the cosine function from 0 to pi is just a decreasing function because just the cosine decreases. The cosine of pi is, let's see, so 1 plus the cosine of x. The cosine of pi is -1, right? So the function decreases down like that, and that's where it is at pi. If I were just looking at cosine x. But since I'm adding 1, it's going to actually go up to 2. It start at 2 and then go down. So it's going to be like that at pi. That's the function. That's the cosine function. Okay, or the 1 plus cosine x. That's this curve. 1 plus cosine x. Now, I want to find the area of the region bounded above by y equals 2 and below by 1 plus the cosine of x. So I actually want this area right here. See, if I had wanted this area, all I would have to ask for is the area under the curve 1 plus cosine x from 0 to pi. Okay? So how am I going to find that? Well, there's lots of strategies that you can use, but kind of for at this level where we are in the book right now, do you guys see a rectangle? Do you see that if you did the area of the rectangle and you subtracted the area under one plus cosine x, you'd be good? Does that make sense? So the area of the rectangle minus this area will give you this yellow area. Okay, so what is the area of the rectangle? Well, it's base, which is pi, times height, which is 2. So that's 2 pi, minus the integral from 0 to pi of 1 plus the cosine of x dx. So this is just going to be 2 pi minus, all right, the antiderivative of 1 plus cosine x is going to be x plus the sine of x evaluated between 0 and pi. So this is 2 pi minus f of b is going to be pi plus the sine of pi minus f of a, which is 0 plus the sine of 0. And so this is 2 pi minus, okay, the sine of pi is 0. The sine of 0 is 0. So this is just 2 pi minus pi, which is equal to pi. So that's the area in between there. So another representation of pi is the area between the line y equals 2 and the line bounded above by y equals 2 and bounded below by 1 plus cosine x. It's kind of funny, I guess. I don't know. And this was from before. Okay. Now let's do some, look at the notation here. It says, express the solution to the initial value problem dy dx equals the tangent of x that satisfies the condition that f of 3 equals 5. Now, the fundamental theorem of calculus tells us that we can construct a function with the derivative a function that is the derivative, or that is an integral, right? And so it says we can construct a function with derivative tangent x. Okay? So there is some function, f of x, which we'll call it like y, such that if we integrate that function from, in this case, 3 to x, we will get, and it should be the tangent of t dt, or some dummy variable. Okay? So that's what this is saying, is that if I take the derivative, do you guys agree now? If I take the derivative of this function that I've constructed, it will just be the tangent of x. Part 1 of the fundamental theorem told us if we go from a to x, that we can construct functions that are the integral from a to x of whatever dt or dx. This was your little f of t dt, and that if you took the derivative of that, you would get back to this little part right here. Okay? So if I now take the derivative of this function, I will get the tangent of x. Do y'all agree? This function that I created, when I take its derivative, will just be the tangent of x. Okay, that's what the part 1 of the fundamental theorem told us. Okay, now what do we have to make sure? That has to equal 5, right? To ensure that f of 3 equals 5, all I have to do is add 5 to this function. Well, let's see if we can convince ourselves that this is true. Because if f of x is equal to the integral from 3 to x of the tangent of t dt, then I need to make sure that f at 3, which will be equal to the integral from, what will f of 3 be defined as? Y'all can do this. I promise you can do this. If this is f of x, how would I write f of 3? Good. I'm going to go from 3 to 3 of the tangent of t dt, right? And then this is plus some c has to equal 5, right? Because this is always plus some constant. So this is what has to be true. It has to be true. Well, what is this? The integral from 3 to 3 of tan t dt.
0.
That's 0. Plus c has to equal 5. So I see then that c just has to be 5. Okay? And so then my function that I create will just be f of x is going to be the integral from 3 to x tan t dt. And you can put a plus 5. You can put it inside here, plus 5 dt. That function now, when I take its derivative, I will get the tangent of x plus plus 5t, and when I plug in 3, I will get, and it, I always get lost on this. But anyway, this function will have the property that that it satisfies the initial condition that f of 3 is equal to 5. And you can see that because if you put 3 in right here, this will be 0, and so you'll get 5. F of 3 equals 5. I need to be, okay, and the derivative is the tangent of x. Okay, so that is it for this lesson.